Hello student, welcome to the web optics course. Today we have lecture number 27 and we will going to discuss about Febry-Perot interferometer. So today we have lecture number 27. So if you remember in the last class we have discussed that if we have a film here like this having refractive index NF, and if a ray is allowed to fall on this system, then it will be transmitted and then again going to this direction. From this surface we will going to have a reflection. From this surface also in principle we are going to get a reflection, and the entire structure will be something like this. This is called multiple beam interference, because these beams will interfere in with each other and there is a possibility we will going to get pattern out of that. So if this is the incident ray I and this is the reflected ray and this is the transmitted one, say IT, then we managed to get a relation, and that relation was this intensity of the reflected ray is the intensity of the incident ray times an expression which is 2 r square 1 minus cos delta divided by 1 plus r to the power 4 minus 2 r square cos delta, where r is the reflectivity of the system and delta is the phase difference that one need to calculate. Similarly, one can have the transmitted intensity in terms of the incident intensity, and one can have an expression like this. R square 1 plus r to the power 4 minus 2 r square of cos of delta. Yeah. So these expressions we calculated earlier, and then we mentioned that what is the maximum condition of this maxima and what is the condition of minima. I am writing this once again. So delta here, as I mentioned, is the phase difference which is k multiplied by the path difference delta, where delta big delta was 2 NF, which is the refractive index of the film, and the thickness of this film T and then we have cos of theta t, where theta t is a transmitted angle this. So, based on that one can calculate delta, and you can see that the delta, small delta, depends on the big delta, and big delta depends on the angle of incidence or the angle of transmittance here with theta t. By modulating this, one can change the phase between these, and one can get the constructive or destructive interference pattern for the reflected or transmitted ray. So, if I do that, before that one can also find that I r plus I t should be the total intensity, incident intensity I I. Now, from this expression also one can see that when cos delta is tends to 1, then IR tends to 0, it vanishes, that is the reflected intensity will no longer be there. That means there is a condition for destructive interference for the reflected rays. So, that condition arises when delta satisfied 2 m pi or small delta, which is 2 n effective t cos theta t, that is equal to m lambda. So, that is the condition one can get out of that. Well, one can also find when IR is maximum and that is when cos delta is equal to -1 or delta is m plus half of 2 pi, or in other word it is 2 m plus 1 into pi. For that particular delta one can have cos delta -1, then IR become maximum. The path difference accordingly it is 2 n effective multiplied by thickness cos of theta t, that is m plus half lambda. Under that condition what we have is IR is equal to 4 r square divided by 1 plus r square and whole square of that I from the previous expression. Similarly, the transmitted intensity will be 1 minus r square 1 plus r square and square of this and II. This one can find from the general expression that we wrote in the previous here. By just putting cos delta equal to -1, one can get these two expression whatever is written here from these two expression, general expression. If I put the condition that cos delta is -1, one can come to this expression. Okay, here one square is missing. I need to put this square. Yeah. Okay, so that was the thing we discussed in the last class. Now we go forward and try to understand the working principle of the Febry-Perot interferometer, a very important interferometer. So today we are going to discuss about the Febry-Perot interferometer. So the setup first we discuss. This is the same setup which we already discussed in the last class, but in a more realistic manner. So where we have, this is a source plane and we have these two blocks. Fine polished blocks. This side is polished in a very high, with very high resolution, right, lambda by 50. So that is the flatness, order of the flatness of these sides, and I will write that. Then we have a system of lenses, and here somebody going to see the pattern. So let me draw how this works here. Suppose I have a source point here in the source plane S, and light is coming here with an angle, and then goes like this and then emits, and then experience multiple reflection here. Like multiple beam interference, and then this ray again come here, and then merge to some point with the lens system. So this is the incident ray, and this is the way the light is reflected back from these two system, which we call the cavity. This angle, if this is theta t, then this angle will be essentially theta t, and these three rays will going to merge by a lens system I call L, and here all these rays will going to interfere. This is the transmitted ray will going to interfere, and as a result what we see here is some pattern. For example, a fringe pattern will be observed here. Maybe it is a maxima, maybe it is a minima, depending on the phase relationship we can find a fringe pattern. My fringe is not looking very symmetric, but it should be a symmetric fringe pattern. So this is the thick glass or quartz whose surface flatness, as I mentioned, is even better than lambda by 50. Lambda is the wavelength of the light that is used. So, very highly polished surface are there. Now, this is the P point where all the transmitted ray is superimposed, and now this point will be a maxima or minima, depends on the path difference between the successive parallel beams. Whatever the parallel beams we have here, these successive parallel beams have a path difference with each other, and that path difference basically determine whether this P point where all these rays are interfering is having a maxima or a minimum. Now, we know that delta, which is a path difference, can be calculated with this. Which is 2D if I consider this air and this separation to be D, then the path difference is clearly written by this expression, and if I consider the in between space is air between these two blocks, if it is air, then ineffective is nearly equal to 1. So, for brightness, at P, one simply have 2D cos theta t is equal to m lambda for transmitted rays. That is the condition one can simply have. So, for a fixed D, you can see that for a fixed D, the condition is satisfied at certain angle of theta, this theta t. So, this condition will be fulfilled by all the points on the circle through. I mean, if I have this source as a circular or a source, a extended circular source, then it should be satisfied by all the points, circular points going through this this point S, and we will going to have a fringe pattern here which looks a circular fringe pattern if the source is circular in nature. So, let me now describe what happened for parallel plate, that we already discussed in the last class. The expression is already there. So, for parallel plate, we have transmitted ray in this form. This is the general form we derived. Plus to the power 4 minus 2 r square cos of delta that is the expression we already had. Now, from Stokes relation, we can have R equal to R prime, that is a Stokes relation we also derived, and R square is 1 minus T T prime. R, the big R, that is the reflectivity, is defined by R square or R prime square. This is the reflectivity, where the transmittivity is defined by T T prime so that that is the condition we have, and we also derived this earlier. Now, adopting that condition, we can write IT as II 1 minus R square we had. So, that will be replaced by transmissivity square divided by 1 minus R square of that. Okay, this is, let me write clearly then. Yeah, so that was class 2 R square 1 minus cos theta. That was the original expression, and I write the original expression in terms of big R and big T. There is a small r and small t. Exploiting the Stokes relation, I am trying to write it in big R and big T. So, this will be T square, this will be 1 minus R square of that, then plus 2 of R, 1 minus cos delta we write 2 of sin square delta by 2. By writing that, I can have an expression like 1 plus 1 by 1 plus, I defined a parameter called f, sin square delta by 2, then multiplied by t square divided by 1 minus R square of that. So, that means I take 1 minus R square common, and then we have 4 R divided by 1 minus R whole square. So, my f that we define should be simply 4 R divided by 1 minus R square of that. This is called coefficient of finesse. It determines basically the sharpness of the fringe. So, the fringe that will generate, it determines this f quantity determines how sharp the fringe will be. Whatever the fringe we have, it basically determines whether how sharp this fringe will be. So, that expression we rewrite. So, for Febry-Perot interferometer, what we have is transmitted intensity is defined as T square divided by 1 minus R whole square of that multiplied by the factor 1 divided by 1 plus finesse sine square delta by 2, where delta is a path difference, and I. F is a finesse, coefficient of finesse, which is determined that where F is 4 R divided by 1 minus R square. This is the coefficient of finesse that determines how sharp the fringe will be. We will show that how to have this. Now, if somebody want to have for maxima, somebody should get the transmitted ray IT should be maxima for under maxima condition, and then this will be, if I put this maxima condition, that means it happens when delta is equal to 2 m pi, m being an integer. That is, in all cases sine square delta by 2 will be sine square m pi, and this quantity will vanish. So, the denominator will have only 1, and in that case IT max will be simply T square divided by one minus R square I. In a similar way, if I want to find out IT minimum, one can get this value sine square delta by 2 should be 1, that is the maximum value one can get for sine, and then it should be T square divided by 1 minus R square of that, and then I have the factor 1 plus F and I. As I mentioned, in that case delta should have 2 m plus 1 pi, that is the value of the delta one can have. Now, what is 1 plus F? This is 1 plus 4 R divided by 1 plus R then whole square of this. and that quantity is, if I calculate, this is 1 plus r whole square, sorry, this is 1, this is not 1 plus, it is 1 minus r whole square. Let me erase this expression here. And the expression simply becomes 1 plus r whole square divided by 1 minus r whole square. This is 1 plus f. Now, once we have the expression of 1 plus f in this way, then readily we have IT max as t square whole divided by 1 plus r whole square I, and IT min is t square divided by 1 minus r whole square, this quantity. Now, from here one can calculate the visibility, and the visibility of the fringes is determined by I max minus I min whole divided by I max plus I min. In this case, if I put all this together, in this case what we get is simply 2 r 1 plus r square. If I put all these values, I suggest the student to please check it by yourself. Just put these two values and then find whether you will going to get this these things or not. So, here also one can find the T max, that is the maximum transmittability, is this maximum transmitted intensity divided by I, and that one can get as t square divided by 1 minus r square. Similarly, T min, the minimum value of transmittivity, is intensity, transmitted intensity minimum divided by I, that value will be t square divided by 1 minus r square. Now, T max minus T min whole divided by T min, that is an interesting quantity one can get, and if they put all these value, if somebody put all this value, it should be 1 divided by 1 minus r square of that, and then minus of 1 divided by 1 plus r square whole divided by 1 divided by 1 plus r square, that is equal to 4r divided by 1 minus r whole square, which is nothing but the quantity f we defined as finesse. So, in this way, today I do not have much time. So, in this way what we find that Febry-Perot interferometer is a system, and in this system works in the principle of multiple beam interference, and we also already calculate when multiple beam interference is there, what is the condition, what is the amplitude or what is the intensity at the transmitted ray for the transmitted ray, and what is the intensity for the reflected ray, and this transmitted intensity and reflected intensity, they depends on the path difference. So, by adjusting the path difference for different launching angle, what we find that in some cases we have maximum transmittability, in some cases we have minimum transmittability, and this maximum and minimum transmittability in the output results in a pattern. If the source are circular, we have circular fringes like we have in the Newton's ring, and what we get out of that is a fringe pattern, and that fringe pattern we also calculate that that fringe pattern depends on something called the finesse, a factor f, and we determine the mathematical form of this finesse factor f. In next day's lecture, we will discuss more about the sharpness of the fringes and the utility of this Febry-Perot interferometer. So, with that note, I like to conclude today's class. Let us meet in the next class and try to understand more about the Febry-Perot interferometer and its working principle. Thank you very much for your attention. See you in the next class.